Today we're going to look at a method for integration called integration by parts. The motivation behind this technique is really to tackle some integrals we just can't do much with. So for example, let's say that you had the integral of x times e to the x dx. Now you can try all kinds of substitutions, all kinds of fancy rules that we have learned, all kinds of add zero tricks that we've talked about. None of them are really going to work. You might be tempted to make a cardinal sin in calculus, and that is to assume that you can just integrate each factor. So I'll write that here in red. So this is a math no-no. So you might assume, oh, could I just do the integral of x dx plus the integral of e to the x dx, and okay, x squared over 2 plus e to the x plus c is my antiderivative. So I'll call that y. Now if you want to double check if you're right, you can always take the derivative of your answer, and if you get the same thing back, awesome, you are correct. However, with a really quick check here, we're going to see, what's x plus e to the x. Yikes, that's not going to work. Also, I don't know why I put a plus there. How about a times? Integral times an integral. So another incorrect logic would be integral of x dx times integral of e to the x dx. That's kind of more what I was thinking. And you will run into a similar issue. You'll get x squared over 2 times e to the x plus c. And a quick check here will determine that, sorry, you're not right, because you've got to use that product rule. Y prime would be x e to the x plus x squared over 2 e to the x, which no matter which way you try to simplify, do any fancy algebra, you are not going to get this thing right here. So then the question is, what do we do? Okay, so the method of integration by parts, in a way, is kind of like a reverse product rule. It's not quite the same, but it's the best that we can come up with. So to show the method, or sort of the pattern, what we're going to do is we're going to look at two functions. We'll call them u and v. So let's say that u and v are two functions that depend on x. And let's suppose we're looking at the product, so u times v. Now, if we were to rewind months ago, back when we were first learning all of those rules for derivatives, if we were to apply the derivative to this, we know that that's going to be, what was that, du dx, so derivative of first times second plus first times derivative of second, so dv dx. Okay, now that was using our product rule. If we were to integrate this thing with respect to x, on both sides, you would come up with, I should say we, since I started with we will integrate both sides with respect to x, so we will get uv equals the integral of v times du plus the integral of u times dv. Okay, so these are all being integrated, or I should say these are functions of x. So v and u are functions that we are integrating. Here this is du, but that's u is also a function of x. So what we're going to do is just a little bit of algebra. We're going to get u dv all by itself. So if you were to subtract this term on both sides, you get the integral of u dv is equal to uv minus that integral of v du. And believe it or not, you might be looking at this and going, this does not look like it's very helpful. But this right here is the method of integration by parts. Essentially, what we're going to do is we get to choose u and dv. So we'll be given an integral, much like that one we started with, integral of x e to the x dx, where that integral we can redefine, or we'll just name some stuff in that integrand in such a way to where we're taking some function and we're multiplying by the derivative of another function, and using this pattern right here we'll be able to integrate that thing. Granted, we're still going to have an integral left over, so I want you all to keep that in mind. Integration by parts isn't really like a silver bullet per se. It kind of is a really useful step in the right direction. You're not done using this first step here. You still have to figure out what this is. So some things to keep in mind. Like I mentioned, we get to choose what we define as u and what we define as dv. So I want to highlight that. So we choose what those things are. Just like when we choose what our function is when we're doing a substitution. Depending on what we choose, that will change a whole lot of things. Some kind of hints. I'll go ahead and write that underneath here. So here's one hint. You want dv to be slightly easy. I'll just put that in quotes because I know that that's a relative term. Also, not a term people like to throw around in education, so non-difficult, whatever euphemism you want there. You want dv to be rather manageable to integrate. Furthermore, you also want u to be something that, I'll put this in quotes, shrinks. Okay, so what I mean by that is, like, it's not decreasing by the technical definition of as y increases, the x values decrease. What I mean by shrinks is, I'll say in parentheses, as you take derivatives. Okay, so basically what that means is u should be a function that once you start taking derivatives, your function gets simpler in a way. So for example, something like x cubed. Okay, that's good because when I take the derivative I get 3x squared. That would be a pretty good choice for u, and maybe not a good choice for dv, because if I chose x cubed as dv, what we're going to be doing each time is we're going to be integrating dv. And we don't want that to grow in a way or get more complicated as we go along. Okay, let me show you how this works in practice. So I'll work 2 examples on this video and then post the rest for another a video that you all can watch after this one. So I'm going to work the one example we looked at a second ago that we started all of this with. So the example that started it all was x times e to the x dx. Okay, so how integration by parts is going to work is you want to choose u and dv. That's actually the first thing you want to do. So I'm going to say u equals, and then I'm going to kind of go down diagonally, say dv equals. And then what I need to fill in is based on what I choose for u, I want to figure out what du, or you can call it u prime, is going to be. And then based on what I choose for dv, I want to figure out what v is. Okay, so just looking at some options, and I'm going to do this in pencil so I can illustrate why you might want to choose one versus another. So let's say that you wanted to choose e to the x as u. So I'm going to put this in pencil because this is actually not the way you want to go, and I'm going to erase it here in just a minute. but this illustrates why you might want to choose u to be one thing versus another. So let's suppose you chose u to equal ex. So you choose u and you choose dv. Okay, so if this is u, the pattern goes, I'm taking the integral of u dv. So since I've already found out what I want u to be, okay, u is e to the x, that means dv is x dx. Okay, because it can't really go any other way. I've got to have the pattern integral of u dv equals, okay, now I'll plug everything in. Or before I plug everything in, I need to figure out what is v based on what I chose for dv, and then what is du. Du, that's pretty simple. Derivative of e to the x, that's just e to the x. Now I need to do the integral of x dx. That's going to be x squared over 2. Okay, so if I went forward with this definition of u and dv, that's going to give me u v, so the pattern is uv minus the integral of v du. Okay, so comparing what I have here with what I started with, things actually got more complicated. It's not any simpler. Also, if I keep going in that way, and I should add to that, a lot of times you're going to have to repeat integration by parts. It's not usually going to go in one step. A lot of times you have to keep going. So right here I have another product, so I would have to use integration by parts again. And that's kind of the issue by choosing dv to be x and u to be e to the x. Even though my u function stays relatively simple, it doesn't get any simpler, and my dv actually gets more complicated. So this is just not really a good way to go. Let me go back and change what I let u and dv equal. That's going to change everything else about the rest of my work here. So I know it's a little messy, but as clean as I can make it. Okay, so instead, as I mentioned, one of our hints, we want u to be something that shrinks or gets simpler, less complicated as we take derivatives. So I'm going to let u equal x. Du is just 1 dx. Ooh, that's much simpler than x. So I need to choose u and I need to choose dv. Those are the first things I do. So dv, I'll let be e to the x dx. Because if u is x, okay, so there's u, then the rest of this has to be dv, e to the x dx. Now to figure out what v is, I've got to take the integral of this thing. The integral of e to the x, that's not too bad, e to the x. Okay, so this thing doesn't get more complicated. This thing gets less complicated. Both of those are good. So if I plug in u, v, so x, e to the x, minus the integral of v du. Okay, much simpler than what I just had. Again, I'm not totally done. I've got to keep going, but it's just heading in a much better direction than what I was headed towards, because the last integral had an x squared over 2 and it was multiplying an e to the x. Really annoying. The last part of this, I just want to take the integral of e to the x. Okay, so x times e to the x minus e to the x plus c. Okay, so you might be wondering, why did you wait to add the plus c till the end? Because I know when we were solving differential equations, you did it like right away, and then you checked your initial condition. Well, here's the thing. When you're using integration by parts, when you're finding v, you're never going to add a plus c. And for the most part, you pretty much hold off on adding that plus c until the very end. Why do you do it? Well, if you put it on earlier, it's going to overcomplicate things, and in fact, it's going to throw your answer off. I know that that's not the best way to put that, but good rule of thumb with integration by parts, do not put plus c until the end. When solving differential equations, when we're using separation of variables and those techniques we talked about, it's a different story. But anyways, here's our answer in case we want to check if our answer is right. So I'll say that that equals y. If we wanted to make sure that our answer is right, so y prime. Okay, first part I've got to do product rule. So that would be 1 times e to the x plus first times derivative of second minus derivative of that plus derivative of a constant 0. Those will cancel. Hey, there we go. That is the right answer. Okay, I know I said I would do 2 examples, but this video is getting long. I'm going to stop here and pick up off here in another video.